Take a blank piece of paper and draw 2 points on opposite corners. What's the shortest distance between them? Your first instinct might be to draw a straight line across the paper. That would certainly work. It's the path we're taught to follow, traveling along the surface from point A to point B. But what if there was a faster way? Now imagine folding that paper so the 2 points touch each other. Suddenly, the distance isn't the length of the paper anymore. It's zero. The 2 points are now in direct contact. Take this one step further, pierce through both layers with a pencil, creating a tunnel that connects them. You've just created a shortcut, a bridge between two locations that bypasses the normal path entirely. This elegant analogy captures one of the most mind-bending concepts in theoretical physics, the wormhole. Just as folding paper can bring distant points together, wormholes could theoretically bend the fabric of space and time itself, turning journeys that would take millions of years into passages that might be crossed far more quickly, at least in theory. It's a concept that challenges everything we think we know about distance, time, and the very structure of our universe. The story of wormholes begins in 1935, just 2 decades after Einstein revolutionized our understanding of gravity. That year, Einstein and his colleague Nathan-Rosen explored the mathematical implications of general relativity and discovered a surprising solution. The equations suggested a kind of bridge between two regions of spacetime, what physicists initially called an Einstein-Rosen bridge. At its core, general relativity tells us that massive objects bend the fabric of spacetime, much like a bowling ball creates a depression on a trampoline. What Einstein and Rosen found was that, under certain conditions, spacetime could be curved in such a way that it mathematically connected two mirrored regions. However, this original version was not traversable and would collapse instantly if anything tried to pass through. A wormhole is essentially a hypothetical shortcut through spacetime. Think of the universe as a vast cosmic landscape. Normally, traveling from one galaxy to another might take millions or billions of years, even at the speed of light. But a wormhole could theoretically connect these distant locations through a tunnel-like structure, dramatically reducing travel time. The structure of a wormhole consists of two mouths, or openings, in a throat connecting them. One mouth might exist in our solar system, while the other could open in a distant galaxy, or even in a completely different universe. The throat is the tunnel itself, the passage through which matter and energy could theoretically travel. Here's where the dream meets harsh reality. The wormholes that arise naturally from Einstein's equations have a fatal flaw. They are catastrophically unstable. They collapse so quickly that not even a photon of light could pass through. In the 1960s, physicist John Wheeler explored this problem extensively. He calculated that a wormhole would pinch off almost instantly. It would exist for only a tiny fraction of a second, far too brief for any practical use. But theoretical physics rarely accepts defeat easily. In 1988, physicist Kip Thorne and his colleagues at Caltech made a breakthrough while consulting on Carl Sagan's novel Contact. Sagan wanted a scientifically plausible way for his protagonist to travel across the galaxy. Thorne's team determined that a wormhole could theoretically remain open, but only if it contained something truly exotic. To keep a wormhole stable, you would need what physicists call exotic matter. This isn't antimatter or dark matter, it's something even stranger. Exotic matter would need to have negative energy density, essentially pushing space-time apart, rather than pulling it together like normal matter does. Does such matter exist? Quantum mechanics suggests that negative energy densities can appear under specific conditions on very small scales. The Casimir effect, measured with increasing precision over decades, demonstrates that certain quantum configurations can produce negative energy. However, the amount of exotic matter required to stabilize a human traversable wormhole would be enormous, far beyond anything we can currently produce or even detect in nature. Some physicists speculate that wormholes might have formed naturally in the earliest moments of the universe, when conditions were extraordinarily extreme. These primordial wormholes, if they exist, would likely be microscopic, far smaller than an atom. They might also be scattered throughout spacetime as part of the quantum foam, the turbulent nature of reality at the smallest scales. There's even speculation that certain mathematical models of rotating or electrically charged black holes could contain wormhole-like structures. These solutions suggest the possibility of bridges to other regions of our universe, or even other universes. However, these theoretical passages would likely be unstable, with intense tidal forces and event horizons that prevent practical travel. Wormholes open another tantalizing possibility: time travel. If one mouth of a wormhole could be accelerated to near light speed or placed in a strong gravitational field, time dilation effects would cause it to age differently than the other mouth. A traveler entering one mouth might emerge from the other, not just in a different place, but at a different time. This possibility troubles physicists because it creates potential paradoxes. Could you travel back in time and prevent your own birth? Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics might somehow prevent the creation of time machines, perhaps by causing wormholes to collapse the moment they could be used for time travel. Today, wormholes remain firmly in the realm of theoretical physics. We have no evidence that they exist naturally, and we're nowhere close to creating one artificially. The energy requirements alone are staggering, potentially needing more energy than exists in entire stars. Yet physicists continue studying wormholes because they sit at the intersection of general relativity and quantum mechanics, two pillars of modern physics that we still don't fully understand how to reconcile. Wormholes serve as theoretical laboratories, helping us probe the fundamental nature of spacetime itself. Whether wormholes exist beyond the equations on a physicist's blackboard remains one of the great open questions in science. For now, they remain beautiful mathematical possibilities, tunnels through spacetime that capture our imagination and push the boundaries of what we think is possible in our mysterious universe. If you enjoyed this journey through the terrifying beauty of space, make sure to like this video, subscribe to the channel, and turn on the notification bell so you don't miss what's coming next.